In this lesson, we're going to estimate areas underneath curves, and we're going to do that just by using simple rectangles. So you can see here I have a curve, perhaps a cubic, we're not sure, and we want to work out the region, the area of the region beneath there. So what I'm going to do first is I'm going to break it up into rectangles, and you can see I can make a decision. Do I do rectangles that touch the curve and just go beneath it, a lower rectangle, or call it inner rectangle because I start at the inner value, or do I do a rectangle that overestimates, okay, an upper rectangle or an outer rectangle because I do start the outer point to draw my rectangle. And you can see one will be an underestimate, one will be an overestimate. And the more rectangles I do, the more accurate I'm going to be. So let's have a look at an example. So I'm asked to estimate the curve, the area under the curve y equals x cubed, from the values of x equals 1 to x equals 3. And we're going to use 4 equal subintervals, which means we're going to use 4 rectangles, okay, 4 spaces, 4 rectangles. And I'm going to do the lower rectangles first. So let's have a think about this curve. And we're going to need to draw the curve first. So the first thing we're going to do is we're going to sketch y equals x cubed. So hopefully we remember what that looks like. Something like this, and then this. Even if you sketch, if you don't recognise the curve, just plotting points will be enough. I'm going to go to x equals 1. What's 1 cubed? 1. And then I'm going to go to x equals 3. And what's 3 cubed? 27. And now I'm going to just draw lines. And this is the area. I'll just dot it so you don't go and can't see everything. This is the area I want to find. Now, obviously, if that was a straight line, I could use trapezia. I could use, a rectangle and a triangle. But we've got a curve. So we're going to need to estimate the area under the curve. So method 1, we're going to use lower rectangles. Now it asks for 4 equal subintervals. So if I drew a line in the middle, that would be 2 subintervals. So now I'm going to go again and again. So there's my 4 equal subintervals. So first, with lower rectangles, in this case, I'm going under the curve for a lower rectangle. And this is called, what did I say, inner rectangle in this case, because I'm starting at the inner value, the first value. So lower is not always going to mean inner. If your curve bends the other way, inner will go above the curve. Okay, so inner, the first starting point. And then inner there, and inner there. So you can see that's going to be quite an underestimate, isn't it? Obviously my scale's probably blown a bit out of proportion, but this definitely will underestimate it. So now I just need to work out the area of each rectangle and add it up. So I know that, the length of each is going to be 0.5. And so the first one will be 0.5 times 1. For the second one, it'll be 0.5 times, how do I get that height? Well, it's just 1.5 cubed, isn't it? I won't work it out, I'll just write it like that. So you could do it as a decimal if you like. How do I get the height of this rectangle? 2 cubed. So it'll be 0.5 times 2 cubed. And finally, for the fourth rectangle, I'll have 0.5 times 2.5 cubed. And then I'll just work them out and add it up, and I'll have an estimate for the area, which we can see visually. In this case, it definitely will underestimate the curve. Okay, so now for the upper rectangle, we're going to use the second value, i.e. the outer value. So instead of using 1 cubed, I'm going to use 1.5 cubed. And instead of using 1.5 cubed, I'm going to use the 2 cubed, then the 2.5 cubed, and finally the 3 cubed. So we'll write that out. We still have 0.5 wide. Put them all down, 4 rectangles. And the first one is 1.5 cubed high. I'll colour that in so hopefully you can see it. Then the second one we'll go to the next value, 2 cubed high for the rectangle. Then 2.5 cubed, and then finally the outer value of 3 cubed. We'll add all those up, and you'll see we'll get an overestimate for the area because all the rectangles now are above the curve. So that made 27 square units. Okay, so let's summarize what we've just done because it's a little bit weird at first. So here I have another curve, and I think this looks like y equals x squared plus 1. Looks like it's been shifted up 1. So I'm going to create inner rectangles. So I'm going to start with 0, draw a rectangle, then 1, go up, hit the curve, draw a rectangle, then the 2, then the 3, then the 4. And this is going to create my inner rectangles, which you can see go below the curve. So my inner rectangles are going to use the first function values to get the height. So from this case here, I've used 0 to get the height. So I've gone 0 squared plus 1. Okay, remember I said that's y equals x squared plus 1. Then to get the height, I've gone 1. So 1 squared plus another 1. 2 squared plus 1. 3 squared plus 1, and finally 4 squared plus 1. Now I'm going to have a look at the outer rectangle. So instead of starting at 0, I'm going to go to the outer value 1, and I'm going to plug that into the function. So the outer rectangles use the second function value for each rectangle. So I'll go 1 squared plus 1, draw my rectangle. 2, so 2 squared plus 1, draw my rectangle. 3 squared plus 1 to get the height, draw my rectangle, 4 squared plus 1, and finally the big fella, 5 squared plus 1 to get the final rectangle. Rectangles that end up going above the curve, like these red ones, overestimate the area. You can see they're always above, okay, because it's all that area. Rectangles that go below the curve, the green ones in this case, underestimate the area. And you won't know this until you sketch the curve. It depends on the bend of the curve, whether you're going to overestimate or underestimate with your inner and outer. So that leads us, how do we improve our results? Well, we could draw a lot more rectangles, and you see the more rectangles you draw, the closer you're going to fit the curve, or you can average your two results to improve your estimate.